So, hi, good morning. Hi. I see most of us were able to connect and welcome back to our class, physics. And I think we are, more or less complete now and we can begin. Let me announce the plan for today. First, we will talk more or less detailedly about your homework solutions, so your test 8 solutions. Today's theory is rather easy, but still important. We will talk about work as scalar product, work as integral, and work as energy difference. Then the remaining time, what we will also discuss is the power. Well, sort of not complicated topics, but still I wish you pay attention to some details. And finally, the remaining time we will spend on problem solving, where I'm going to give you some new interesting tasks, maybe more challenging, also from the range of dynamics problems. In particular, what I would like to try to do today is solving problems where ropes have mass. So before, we only solved problems where ropes were massless. And today I would like to try with you maybe one or two problems where we'll use real ropes. That means our lines, our connecting ropes will have mass. And already I can tell you what expects us next week. We will have class next week as usually, although here most of my lectures will be already done. So in FH, most of our classes are canceled, but our class will still take place. So we will meet next week. Please do not forget it. And our class next week will be devoted to centripetal acceleration and the forces acting in a case of circular motion. So that will be a separate chapter. Let's call it Christmas chapter. We will talk about circular motion and centripetal forces. There will be just two formulas that we need to know from that class, but it will be useful for us as we later proceed with energy conservation problems. So let me put it here. So our schedule for today. So first we have homework. Second, theory. Work. Power. Third, we will do some advanced problem solving. And fourth, it's just next class, next week. Let me just give you two keywords. So that means what your additional homework is gonna be is to take a look in the book chapters, whatever book you use, Stifler or Halliday or Stewart. You can check the theory concerning work, which will be not much and it will be not stressy, and most of you even don't need. And if you want to prepare yourself better for the contents of next week, you can already take a look and just, go through quickly the topics like circular motion and centripetal acceleration. Okay, das ist unser Plan für heute und der erste Punkt ist die Hausaufgabe und der Test. Ja, hier möchte ich erstmal mich bedanken bei denjenigen, die die Hausaufgaben gemacht haben und mir geschickt haben. So, thank you to everybody who did your homeworks. Again, let me just announce that so far I got solutions from Mbam, Tirt, Patel, Anthony, and Alireza. And that's it. And it's not much. Thank you. I want to thank these people, and I want to ask all the others, please think about sending your homeworks to me. I never pressed on you. I never said it is a must, but slowly it will be must, because if you haven't sent much till now, you have a problem, because later you get problems from me, from our administration, and so on. So think about this, sending your homework solutions to me. Even if you don't have any access to Iliad system, this should not be the problem. You can send it to me either by using my email address that I've given to you many times, or by using Iliad system, or maybe you can also try over EduPage. But honestly, I don't have like EduPage account, so that's why I'm not sure that I'm getting emails over EduPage. So in the case, if you have some hesitation, please still just use my working mail address, diegel@fhaachen.de, and please don't forget to send your test solutions to me. Again, just in case, let me repeat it. My email address, diegel@fhaachen.de. So I checked your homework solutions. Most of them are pretty good, not perfect, but pretty good. That gives me signals that you are good on a way, that if we work further, then you have a good chance to pass all necessary tests. And for people who haven't sent nothing, I cannot say anything, and yeah, this is the problem. Don't be afraid that you will, blame yourself. Just show me where you are and how good you are. So from today's class, again, we will have one more homework, one more test, which will again consist of 3-4 problems, and I want you to take it seriously. It is not for me, it is for you. Okay, jetzt sollen wir kurz überlegen, was die Lösungswege waren. Und jetzt schalte ich auf mein anderes Programm und wir schauen mal gemeinsam, wie die Lösungen sind. So you've already noticed that I try to accompany most of your tasks with German versions, so that you first try to learn and to translate the German version, and then the English version serves as a sort of additional help for you. So please use these tasks this way. So read German version first, try to use the German version, and English is just a sort of supplementary, just supporting. Aufgabe Nummer 1. Polysysteme mit einer, 2 oder 3 Rollen sind neben dargestellt. Vernachlässigen Sie die Gewichte der Rennscheiben, ermitteln Sie die Kraft, die erforderlich ist, um das Gewicht W in jedem Fall zu tragen, ohne Beschleunigung, und begründen Sie Ihre Antwort. Okay, scheinbar ist das die gleiche Aufgabe, die wir vorher gelöst haben, zumindest Fall A, ist das doch genau, was wir vorher besprochen haben. Das heißt, gibt es hier an der Stelle eine Kraft W, dann wird diese Kraft links und rechts verteilt, und zwar 50-50. Das heißt, auf der linken Seite haben wir W durch 2 und hier W durch 2. Also Hälfte, Hälfte. Ist ja logisch, ja, das haben wir schon gelernt. Das heißt, hier an der Stelle wird Tension of the rope, wird die Zugspannung W durch 2 sein. So, was passiert denn hier im Fall B? So let's check the B option now. So again we have V, this is the only force that acts downwards, and it is opposed by multiple pulleys, and again if we separate this force this way, then this part should be V divided by 2, and this should be V divided by 2. Then in fact here we have one more branching, one more separation, which means further division, and again we have V divided by 2 divided by 2, which is V divided by 4, and here we have V divided by 4, 2. So that means in this case tension will be equal V divided by 4. And the same procedure we can apply in the next case and all other cases, remembering that it is sort of branching, it's sort of like a tree, and every time you have this division by 2 procedure. So overall, we see what happens. If we have 1 pulley, this will be the answer. 2 pulleys, this will be the answer. 3, this will be the answer. What we see here is this number can be probably formulated or theoretically expressed as 2 in the power of n. And this is what some of you suggested in your solutions. I think I can agree with you. I think this is a good way. That means, in average, if we have n pulleys, then the tension will be equal 1 divided by 2 in the power of n. And that means in a case of 20 pulleys, the tension must be equal 1 divided by 2 in the power of 20. So if you calculate it, this is fine, but if you don't, it's a big number. And I think this is the way how you can algebraically model this system. Also eigentlich eine ganz einfache Aufgabe. Die meisten haben zumindest 2, 3 Schritte geschafft. Das haben sie gut gemacht. Mit dem 4. Schritt haben manche ein bisschen Probleme. Ist nicht schlimm, aber das ist, was wir üben. Ja? Wir üben ihre Fähigkeit, auch mathematische Modelle herzustellen. Jetzt bewegen wir uns in die Richtung Aufgabe Nummer 2. Und auch hier gab es ja gute und nicht so gute Ideen. So again, let me remind you what we do and how we do it. And again, I was pretty glad to see that most of you, actually all of you who sent your solutions, you actually applied the algorithm we introduced in our classes. That means this drawing of forces it works pretty good. So you did it really good. I liked it very much. And that means at least for that point, you will get points in your test. So let's put it again. We have gravity force. Let's call it mg. We have normal force, which acts from the surface, right? And we have friction force, which presumably may act either upwards or downwards. So actually, with the direction of friction force, let me leave it still alone. I will put friction force and I will put it here like question mark, because this is what we need to discuss a bit. But first, I would suggest that you solve this problem without using friction force. So let's do it. Just forget about friction force for a while. So what if I have just two forces? It is about this direction. So we're interested in movement of this direction. That's why it is logical to make this axis our main axis. So you choose this direction as positive. It makes sense because you don't know the end force exactly, and you are rather interested in the motion along this axis, so that's why it makes sense to make this direction positive. So now, if you project your gravity force to this axis, the only component of gravity that is interesting for us will be this arrow. So this component of gravity force, which will be mg sine phi. Since it is 45 degrees, basically it doesn't matter. We can use sine phi or cosine phi. They are both equal. Well, now, what is the force you need to apply them to compensate, to cancel the force mg sine theta? I think it's clear we just need to apply equal force. So the force we should apply, we should act is equal mg sine phi. So that means we are, without using any friction first, we can find the magnitude of the force you need to apply to your body, which will be equal, this we know, with this we know, this we know. So 20 multiplied by 10 multiplied by square root of 2 divided by 2, which gives you, well, let's make it like 100 square roots of 2, which is actually close to 141.4. But if you leave it like this is fine. I mean, it doesn't matter. So that means we haven't solved this problem, but we partially solved it without friction force. Now, what we can do, we can find friction force separately. So what would be the maximal magnitude of friction force that would be possible here in our system? Maximal friction possible. For that, we just need to apply the formula we discussed before. Friction force is friction coefficient multiplied by the normal force. Again, let's use the triangle we see here, our drawing, and here we see that n can be expressed as mg cosine phi. That means the friction force will be equal friction coefficient, which is 0.2, multiplied with mg cosine phi, which is n. How big it is, how much it is? Well, this we know, this we know, this we know, this we know. We can calculate, which will be equal 0.2 multiplied by 200 multiplied by square root of 2 divided by 2, which will give you 20 square roots of 2. Okay, we found the maximal value of friction force without specifying its direction. Here you may disagree and you may say, wait a moment, how can we talk about force without specifying its direction? We need to know the direction. Well, please wait a moment, and we first found the magnitudes of forces acting in our system. So we found the magnitude of force we require without friction, and we found the friction magnitude. So these two formulas, blue one and the black one. And now we approached one pretty important and crucial step where you need to think carefully how exactly you apply the values. And in this case, please use your imagination and think about real systems. So just think about such a block and you use your finger to stop this block from motion, so to prevent it from moving. And this is your friction force. Now think about if you apply precisely the blue force we've shown here. Will it move? No, it will not move because both forces are perfectly equal to each other. And actually, the friction force in your system will be zero because there is no force that tries to move your object. Both forces, downwards and upwards, they are perfectly equal, and the friction force will be zero. Okay, and this will happen if your force will be exactly equal to mg sine phi. Well, but what about if you make this force a little bit less than mg sine phi? So you still use your finger, but you make it a little bit less. Just maybe 1 micronewton less. Of course, in this moment, the friction force will be born, it will appear in your system, and it will oppose you, and it will still prevent body from moving. So then you make this force less, and even less, and less, and you just study how big or how you can decrease your mg sine phi in order to reach your body moving. So, and it is logical that the smallest force you can apply or that you must apply will be your force minus friction force. So, if you have this condition, if your force is close to that value, still it will not move, but it will be now starting moving. So it will be going to move. On the other hand, if you increase your force in your finger and you try to shift your body, the block upwards, this block you are shifting upwards now, again, it will be friction force which will oppose you, but this time it will work in opposite direction, not downwards, but upwards. No, oh, wait a moment. You are shifting upwards. No, friction force will work against you downwards. So, and again, the value you will reach will be equal to F plus friction force. And that means that we are getting the answer. In this system, the minimal force you may have will be 100 square roots of 2 minus 20 square roots of 2, which is 80 square roots of 2. And the maximal force you can have in the system without having it moving is 100 square root of 2 plus 20 square roots of 2, which will be equal 120 square roots of 2. And these are two answers. Of course, if you express them as numbers, it's not a mistake, it's not bad. So 80 square roots of 2 is equal 113.13 Newton, and 120 square roots of 2 is close to 169.7. Please take a look, please think about this, and then if you have questions, please just raise your hand or give me a signal. We can switch your micro, or you can write something in the chat. If you have any question, if you have any doubts related to this problem. And if I get nothing from you, or if you say it's all right, then we proceed to the next problem. In my opinion, in the problem number 2, the only challenge was to consider that the friction force can actually work in both directions, right? So again, it may work upwards or it may work downwards. So it can be applied in two ways. And that's why we needed, in the first case, we needed to add it to our pure force. And in the second case, we needed to subtract it from our pure force. And that's why in our answer, we need to deal with two values, with the range of values, with minimal value and with the maximal value. So I'm just giving some time if you want to write it down. And actually, as always, I'm recording this class. So the video recording is still running. Sometimes it fails, so mostly it works fine. And I think it always can help you just to take a look in the video. But in some cases, video may fail. So that's why it still would be advantages for all of you if you take notes, if you really make your own notes. Then in this case, you will not depend on video records. Okay. So, well, so far there were no messages from you. That means I assume everything is okay, so that you have no questions related to the problem number 2. Of course, if you later still have some questions, we can clear them. But let me now erase see. Make some space here. Okay. So let us move to the next problem. Again, problem number 3 was one of the classical setups you may have on your test. Mostly those problems appear in the midterm exam, sometimes in a final exam as well. Although final exam mostly deals with rotational dynamics, but elements of statics still appear even in your final exam. That's why I want you to be good at solving problems that involve statical equilibrium. That means non-moving parts and calculating the balance of forces. Let us check the task and solution together. It was made totally in German, and I hope you could understand it completely. Let us check it. Eine Straßenlaterne mit einer Gewichtskraft von 50 Newton wird von 2 Steilseiten in einem Winkel von Alpha gleich 25 Grad gehalten. Wie groß ist die Kraft im linken bzw. im rechten Seilstück? Let me translate. A street lamp weighing 50 Newton, which is its weight, will be supported by 2 steel ropes that have angle alpha equal to 25 degrees with respect to horizontal plane. How big is the tension in the left and in the right rope? So our task is to find tension in the ropes. So this one and this one. Let's call it T. And first of all, for symmetric reasons, I think it is legitimate and it's right to assume that both tensions are same. I think this is what you agree with, right? So they should be equal because it's a totally symmetric system. So we are not searching for T1 and T2, but we are searching for one single T value, which is equal for the left and right side. Next question. How big is the Ty value in y direction? So this is y direction, and this will be x direction. How big do you think should be the sum of these values? T plus T must be equal precisely to the weight of the lamp, right? Because the sum of all forces acting in upwards direction, it must be equal to sum of all forces acting in downwards direction. Why it is so? Because it does not move, right? So these forces acting in downward direction, it is just only weight, and it's equal to 50 Newton. That means logically, the Ty plus Ty, these components, this Ty let me put it blue, and add it to this Ty, which is also blue, they together result or sum up to 50 Newton. Logically, that means that they must be equal 25 Newton each. I think it's logical, right? If you think about this, you would agree that Ty in left side and also Ty in the right side are both equal to 25 Newton. Seeing mathematically, you can make it like this. We have two vectors, this one, and each of them are equal to 25, and they add at vectors. What you will have if you have two vectors added, they will sort of add head to end, right? And the resulting vector will be 50 Newton. Everybody agrees so far? We made two steps in the solution. First, we said tangent in the left part is equal to tangent in the right part, must be like this. Second, we found out that the vertical components of tangents are equal to 25 Newton. They must be like this. They cannot be different. Next, I would like us to check this triangle. Let's take triangle. Let me make it black. This triangle. So what we have in this triangle, this angle is equal to alpha. This is the horizontal component of the tangent, and this is vertical component of tangent, which we already found. Now look, we know the angle, we know the vertical component, and we can find the horizontal component now. From this triangle, we can write Tx divided by Ty is equal to cotangents of alpha. Which is cotangents of 25 degrees. Or if you wish, you may it vice versa. You divide Ty by Tx, and in this case, it will be tangents, yeah, tan alpha. But I did it this way. So that means Tx must be equal to Ty multiplied by cot alpha equals 25 multiplied by, what is cotangent of 25 degrees? It is 2.14. 2.14 equals to 53.61 Newton. Great. So we found now both the x component of tangent, which is 25 Newton, y component, which is 25, and it is here. And we also found the horizontal component, which is 53. I think the remaining step is quite simple and clear, because we have in the triangle, we know two arms, two sides. We know this side and we know this side. And the aim is to find hypotenuse, which is clearly equal T is equal square root of Tx squared plus Ty squared. So Pythagorean right? Theorem. So let's find it. Square root of 25 squared plus 53.61 squared. Approximately should be equal, I think, 59.15 Newton. I'm not sure. I didn't do it on the calculator. I did it on the paper, so I need to check it. Okay, so please take a look. Again, I give you, please use time, a couple of minutes to think about solution. If you have any worries, if you have still some unexplained things, please just use this time. Meanwhile, I will check the questions you sent. Okay, thank you, Emmanuel. Thank you for this, for this message. That's fine. Everything is fine. So take your time. It would be great. I would be glad to get the solutions from you. So thank you for this message. Then I will waiting for your solutions. Good. So you agree. Okay, thank you for this feedback, Mom. So it means that we are close to this value. Fine. For the others, let me again summarize, or let me make it a bit in German. Ich möchte jetzt ein wenig zusammenfassen, was wir bei dieser Aufgabe gemacht haben. Und zwar wichtig ist, oder wichtig war dabei, die Kräfte in unserem System zu spalten, also zu zerspalten in Komponenten. Also anstatt mit Zugspannung zu agieren oder zu handeln, haben wir diese Zugspannung in zwei Komponenten zerlegt. Und zwar Tx und Ty. Und wir haben dann unabhängig voneinander Tx gefunden, also x-Komponente, und y, also y-Komponente. Und meistens ist das eine gute Strategie, wenn Sie bei solchen Aufgaben immer die Kräfte zeichnen, dann die Richtung definieren und dann mit Komponenten arbeiten. In unserem Fall waren es X- und Y-Achsen und wir haben erstmal alles für die Y-Achse gefunden und dann haben wir das Ganze für X-Achse gefunden. Und zum Schluss haben wir das einfach benutzt, um die ganze Magnitude von Zugspannung zu finden. Tim, thank you for your question. You used a different method, which was totally fine as well. I think if I remember it well, you used some sine and cosine things, if I have it right. But you are right, in solving this problem, it is absolutely legitimate and plausible to use another trigonometric functions, and this is totally fine. Yes, so for your solution, you would also got same amount of points. You did it also well, and you did it correctly. So don't worry about this. And this is the advantage we all have in our physics course. In fact, in the end, it doesn't matter which exactly way of solutions you use. As long as it is possible, scientific, and understandable, you will get good notes and you will get good answers. The answers I'm showing to you are maybe not always optimal, but at least one possible answer. So I'm trying to share my vision, my experience with you, and it is but absolutely fine if your solutions may be somehow different from theirs. This is totally fine. And by the way, as we are checking your exam results, your solutions in the tests, in the exams, we always try to understand the way you solved it, your logics, your approach, and sometimes even physics teachers, they make discoveries. They say, wow, that was a cool solution. I haven't expected that this problem can be solved this way. Sometimes it happens. So sometimes we have very talented students who solve our tasks in some unexpected way, non-traditional way. But still, if it's as long as it is correct, as long as it is scientific and mathematically correct, everything is fine. So now, before with the break, we have approached our last problem in the test. So traditionally, you notice that I am putting a bit more challenging problems to the end. So the problem number 1 was actually too easy. Number 2 was okay. Number 3 was also possible, but if you do it carefully. So problem 4 is a little bit more challenging. So that's why I even put like an asterisk to it. You see, there was a sign showing that this problem might be a bit more challenging. This is a signal for you also that if you were not able to solve it, it is not too bad. In fact, we expect that such problems will be solved not by all students, but only by students who really spend time and understand and already are at high level. But you do not necessarily have your high level right now. That's why we're spending time together and I'm explaining many things in order to bring you to this level. So, and if you are not there still, it's not a problem, we still have time. On the other hand, this problem wasn't very challenging in fact. Let me now show some ideas behind. I will explain how I would solve it. And after that, again, I will give time to you so that you can check if you agree or if you don't agree, if you find any troubles or mistakes, or if you have any questions, and then we can discuss a bit about it, okay? Let me use the algorithm we used always before. So I would suggest you proceed always with the same amount of steps. So first thing I will do is to making force diagrams for mass M and for mass M large. And this is, by the way, what many of you did who sent me your homework solutions. You did it well. Thank you very much for that. It was a good feedback for me. So what about M? So in other words, what are forces acting on this upper mass M? Obviously, gravity. Obviously, it is a tension from the rope. Let's put it here, T, T, T. Since it does not move in upwards, downwards direction, the mg force is perfectly compensated by normal force. We already can say that normal force is exactly equal to mg. So force up, force down must be equal to each other, both mg. And finally, and this is where some of you made mistake, please be careful here. We need to address the friction force here carefully. Also, good students made mistake here. Please notice that since the tangent is pulling the body m small to the left, the friction force will bring it to the right, right? So we can make friction force showing in this direction. I can draw it from the center, it's not a problem, but I wanted to make it more visible, so that's why I'm drawing it here downwards. It's up to you, it doesn't matter, because we're dealing with point-like bodies, and you can draw forces whatever you like. So if you don't like it this way, you can also write it this way. It doesn't matter, actually. Now, that was it, actually. That was all forces acting on the small mass. As always, if you have sudden questions that needs to be cleared right now, you just click the hands button, and then we can talk about, okay? But it would be also nice if you don't interrupt, so I will finalize the explanations. Now m large. Well, here please be careful, because in vertical direction we have first of all its mass, its weight m large g. It has also some force, the weight from the smaller body, that means m small g, right? So I have double load on the ground, not double but increased load from both bodies. And this will be opposed by reaction force, let me call it R, which will be again balanced. It will balance the gravity forces. That means R will be equal m small g plus m large g. Okay, from vertical direction it is clear. What about horizontal direction? Here we have also interesting combination of forces. We have, on the one hand, it will be tension that tries to move this body to the left. We have our pulling force, F, which tries to move it to the right. And please don't forget, there will be also friction force in your system, which will work in which direction? Maybe somebody can comment. This body m large will also experience friction force. In which direction the friction force will act? To the left or to the right? Well, yes, the friction force will be coming from the smaller body, and it will act to the left, because this is the friction force which appears on the interface of the body m small and m large, and it will equally act on small body and large body. So this was actually one important step that some of you haven't considered. So friction force acts equally on the m small and on m large. It must be like this. If you think about it, you have two bodies that are contacting to each other, and if one body exerts friction force on another, then the other body should also exert friction force on the first one, right? It must be like this, and by the way, this is what is postulated by the third Newton's law, right? So That's why now, after we ready with this first step, we can think about choosing the right axis for our solution. I would suggest still because the whole system moves sort of this way, I will choose this as positive direction. So let me make it more clear here. I will choose these axis will be my positive axis. So I will just follow the rope. I will follow the motion of my system. So these will be my curved axis, and it will be positive. So I will now put all projections of my forces, and I will project them all on this axis. Let's do it. So for the body M small, how the second Newton's law will look like. By the way, let me write it again. Sum of all forces acting on this body will produce its acceleration. So what is it about smaller body? What acts positively? Tangent. It is opposed by friction force, which is equal mu mg. The force mg and mg, they act on vertical direction, and since they are perpendicular to our axis, we can forget about them. They are not interesting for us. So that means that was it, equals ma. That was it. What about m large? Again, let's check what is positive, what is negative. Positive is the force F. So this one. It is opposed by friction. Again, also friction tries to stop another body. And it's opposed by tangent. And it results in acceleration of the large body. Some of you may ask about why it is here mu mg small, not mu mg large. Well, if you think about this, you would agree that it must be mu mg small because it is not the weight of the bigger object that is related to the friction force. Since there is no friction between the large body m large and background, there is no friction here. Let me show here, no friction. Then the only force of friction which appears in our system is here, and it is caused entirely by the normal force produced by the smaller body. That's why this force, also for the larger body, it is mu m small g here. It's still same friction force that acts between these two bodies, okay? And now we are ready with these two equations, and our goal is to find the force required to make acceleration equal to 5 meters per second squared. Well, I think it's quite easy to solve this system for F. I would suggest that we just take first equation and we add it to the second equation. So let's plus them. What we will have is T minus mu mg minus plus F minus mu mg minus T equal ma plus m large a. T and T cancel. What we will have is F minus 2 mu mg equals a m plus m. F is equal a m plus m plus 2 times mu mg. And now I think we can put the numbers. F is equal 5 multiplied by 1 plus 2 plus 2 multiplied by 0.5 multiplied by, is it 1? 1 multiplied by 10. 15 plus 20 equals 35. No, it's 10 plus 10. 25. 25 Newton. I think that should be the answer. Again, let me give you some time to think about this, to check the steps, to check if there are any mistakes or any places where you have doubts. I will still try to save this. Speichern. So I can also forward it to you today after the class. Alles klar, alles gut? Oder haben Sie Fragen? Haben Sie noch irgendwas, was noch fehlt oder unklar ist? Okay. I have no messages. That means I assume that you are fine. I hope this problem solving we did together, that it was helpful and useful for you. Even so, maybe there were some things that you now understand better, I hope. And my recommendation to you, to all of you, will be, doesn't matter how good you are in physics, since we are trying to achieve the goal to make your study at Fachhochschule Aachen easy and smooth and less problematic, I would strongly recommend to use this time you have now to work hard, to study hard, to load yourself daily with intellectual tasks. I know that every one of us has different situations in a family, financially, and so on. But to what extent it is possible to you, just use your brain, exercise your brain, make your brain into a sharp instrument, into a sharp tool, because in your future, I think you don't want to use your body as your main working tool, but you want to use your brain as your working tool. And for that, your tool, your instrument, must be sharp, must be in the perfect state. And for that, you need to exercise it. And you can perfectly exercise your brain by solving physical problems. You've already discovered that in physical books, there are lots of dynamics problems you can just solve even for fun. And then you have triple win. First, you make your brain better. Second, you improve your chances to get a good note in physical class. Thirdly, you also make your later study, much more easy. So please use your time efficiently. You are young, your brain has highest performance now. As I'm teaching neurology, I know that starting from the age 23, our brain is starting aging. It sounds quite sadly, but beginning from the age 23, our brain stops developing and starts dying, in fact. So now, since you haven't reached this age, your neurons are better, they have better performance, and this is perfect age to learn science, to learn languages, and to learn some social competences. Because later in your life, that might be less easy because your brain is not so fit. Starting from the age 23, our brain daily loses 20,000 of neurons. It is the population of the whole Jülich, for example. And this is a neurophysiological fact. So my main message to you, all of you today, is use your brain, exercise your brain, and use it now, because now you have the best possible position for that. So there was a question from Omar. Thank you for this question. In the books, there are no answers. I can make sure I'm right. That's fine. And this is why I'm here, and I am ready to check some situations together with you where you have doubts. Please don't worry and hesitate if you have some solution and you are pretty interested to know if your solution was right or wrong. You can send your solution to me. You can take a photo and send it to email. I can take a look. I can check it. Some problems are really funny, and it makes fun to solve it together with you, and I can give this feedback. So why not? Yeah, on the one hand, I must admit I am a busy person, since I'm a director of institutes. I'm head of 2 laboratories, and I'm giving 80 hours of lectures in master courses. I'm teaching PhD students and many other things. But still, for such things, I always try to find time. So you are invited to send your solutions to me if you find interesting problem, and if you don't know if your answer is correct, send it to me. I will check it and we can discuss. So now let us make a break at this place. 15 minutes long, that means till 10 o'clock. Please relax and take your time after the break. At 10 o'clock in German time, I mean, we meet again, and we will talk about different aspects of work, of physical work, and what's the exact difference between work and power, and how we use it in problem solving. Okay, so enjoy your break, and we see us in 15 minutes. So now I switch my microphone, but if you still have something to write, to share, you can use the chat window still. So see you in 15 minutes. Hey, sorry, there was a little additional telephone call. Sorry for this interruption. Ich hoffe, wir sind alle wieder da und jetzt geht's weiter. So let us proceed with our little theoretical topic for today, which I already announced before. It is called work as as scalar product, work as integral, work as change in energy. So we're going to discuss briefly about three different facets, three different aspects of work, so that you have broader and deeper understanding of meaning of work, how you calculate it, and so that in 2 weeks you can more easily apply the concept of work for solving problems in the frames of energy work theory. So we are slowly preparing for the coming topics with you. Today's class theory is quite easy, and I hope that you enjoy it, and still you will find it somehow, not only, just physics must, but also useful and helpful. So let me switch back to my drawing program, and then I will explain the things. Okay, so today we'll talk about work. I think everybody know already that work in German is Arbeit. Also die Arbeit. You have lots of German words in physics that are related to the word Arbeit. For example, Reibungsarbeit, the work done by friction, or elastische Arbeit, the work done by elastic forces, there are many examples where the word Arbeit will appear in physical terms. Okay, but what is work? Let's make some general definition of work. Assuming we have an object having some displacement vector r, it can be in three-dimensional space, so it will be like having 3 coordinates, one position, and it's now shifting its position, so we have some displacement. And this displacement occurs due to action of some force. And let this force be whatever, F. And force is a vector as well. So, and then the concept we will use in the future will be, just a moment. Okay, so we'll use in the future will be how much work is done by the force. So obviously this displacement is caused by the work, but how much work is done by this force. And in this case, they have introduced in physics a special value, which is we say that we have these two vectors, vector r and vector f, and we multiply them as scalar products. So please notice that here we have scalar product. That means if we are talking about vectors, then in mathematics you would maybe write it like this. So x, y, z, and it will be multiplied as scalar product to some f, x, f, y, f, z. And well, I think from mathematics you remember how you make it. So in fact, you multiply and you add the values. So in the final, as the final answer, you are getting a scalar, one number. And this scalar, this only one value that you have here is the work. In other words, work cannot have any direction. It cannot be in any direction because it is a scalar. It is a single number, single value. But the work may be positive and negative. And this number you are getting may be positive or negative depending on what the scalar product of these two vectors will be. Since we are talking about work value, I think you also remember how we calculate the magnitudes of work, right? So if you're talking about work, we can simply take the magnitudes of the corresponding values. We take displacement magnitude, we multiply it with the magnitude of force, absolute value of force, and we needed to multiply it to the cosine of the angle between them. Let's call this angle theta. So it will be multiplied by cosine of theta. And I think slowly you can recognize the formulas you've already learned also in your high school probably, which is in order to find the force, if you have two vectors, the vector of displacement, so the vector of motion, and the vector of the acting force, you take the magnitudes of these two vectors and multiply them on the cosine of the angle between them. So this is the first part of today's theory. So what we've done now, we've defined work as scalar product, and we have this useful formula that we're going to apply later in the problem solving. The formula is quite easy, and I think you have no difficulties in applying it in the case of scalar and vector situations. In fact, what follows from this formula are two important consequences. The first consequence, the first conclusion is if the displacement vector are parallel to the vector f, we say that the angle between them is equal to 0, and in this case we just define work as the product of r multiplied by f. I think again this is a formula that all of you know. Sometimes instead of r they use puff, right, or way, so you may have seen it like s multiplied by f, or in some cases they say it is L multiplied by F. Well, it doesn't matter, right? So in all cases, we know we are dealing with force and we're dealing with distance. So in the case, they both act in the same direction. We just simply say we deal with simple products of these two numbers. If they have some other direction, then we have to consider the cosine of the angle between them. So the second consequence we have to deal with is also an important one. And this is the case where your acting force is perpendicular to the displacement. In this case, we say that cosine angle is 90 degrees, pi over 2, and cosine of 90 degrees, as you all know, is equal to 0. In this case, even though there is a force and it acts on this object, in this case, we say that although there is force and there is motion, there is no work done by F. Because the formula 1, which I will put here, will give us 0 F work. For some of you, it may appear obvious. For some of you, maybe not, but in any case, it is worth it to keep in mind because later we will meet this second case also many times. And please be aware that in the case of acting force being perpendicular to the displacement, the work done is 0. Let me give you just one example. If we are talking about moon orbiting the Earth, so we all know that the moon is following circular path or elliptic path around the Earth. And obviously, the gravitational field of the Earth is acting on the moon. So, and it is causing this motion. So, in fact, if we remove the gravity from the Earth, the moon will not be orbiting the Earth anymore. It will fly away. So, but still, because, let me make a drawing, this is the Earth, and this is the moon, and this is, let's say, the motion of the moon, because the displacement of the moon, the displacement vector, the motion vector, is perpendicular to the gravity force vector, we say that the work done by the Earth on the moon is 0. So this is just one, I think, example where we have this situation. There is motion, there is force, and the force causes this motion, in fact, but the work done by this force is 0. And this is good so, because if it would be different, it would mean that since gravity is doing work, it consumes energy. And if energy is consumed, someday it might be depleted and it might be over, and then it will be, not happen anymore. But since the gravity of the Earth is not doing any work on the moon, such a system can exist sort of forever. There is no energy consumed in the system, and that's why the system can persist for a very long time. In ideal case, forever. Now let's shift, let's move a bit to another topic, and let us now experience yet another phase of work. It is not only a scalar product, it is also an integral. Let me explain why. If you simply plot the, let's say, displacement and if you keep the force same, so you have constant acting force, and this acting force does some work, and it caused this displacement to happen. So I'm plotting the graph force as a function of displacement, and it remains constant over time and over displacement. Then I can calculate work as product of force and displacement. That means here I have force and here I have displacement. And logically, the product of them will be the square of this figure, right? So I then will have a case F multiplied by R. It is, since they are vectors, again, I'm talking about the product of two vectors, and I'm talking about scalar products of two vectors. Well, but strictly speaking, my force does not need to remain constant over time. It may vary, it may change quite abruptly. And in this case, I need to be a little bit more careful. Let me give you now one more example that we can analyze together. Let's consider a nail. Just a moment. Sitting in a wall. So there is a wall, wooden wall, and there is a nail. The length of the nail, let's call it L, will be 10 centimeters. And now you want to pull it out of the wall. And at the moment you try to catch it and pull it, you notice that the force you require is quite a lot. So you need to apply force equal 1000 Newton. Wow, that is a lot. So now if I would ask you, please calculate how much work you need to do in order to hold this nail out of the wall. At first glance, the problem seems to be easy, right? So you say, well, it's sort of easy. I have L, which is equal 0.1 meters, so I have my displacement. I have my force, which is 1000 Newton, and we talked today that work is a scalar product of work multiplied by displacement multiplied by cosine of the angle between them, but in this case it is cosine of 0. That means the formula will collapse into F multiplied by L. Seems to be fine, but it is a wrong solution. It is not correct. Why it is not correct? because our force does not remain constant. So you cannot apply this formula. Instead of that, you need to consider that the force will change, because all of you know if you start pulling the nail, the friction between the nail and the wall will be less, so you will need less and less and less force to pull it out until in the end you actually do not need to pull it much. It sort of goes by itself, right? So in the end, as it is almost out, you have zero resistance force, right? How do we consider it? Let's make a graph. I will plot my force now, force I need to apply as a function of position. I am starting from 0, and at this moment, as I'm just starting pulling, my force is 1000 Newton. And what is in the end, as I am 10 centimeters away, that means my nail is already out of the wall, and logically, in this case, the force will be 0, right? So I think we dare assume that the function is linear, so that means it is a linear relationship between my position and force. That means the further am I with pulling, the less will be the applied force in a linear manner. And in this case, we say that the work we need to find is this area below the curve. In other words, let me show this. Instead of using this maximal force equal to 1000 Newton, you say, no, this is just initial force, and my final force is 0 Newton. So instead of using initial force or final force, I will use the average force, right? So I will introduce average, which will be 1000 plus 0 divided by 2, which will be 500 Newton. So that will be my average force for my calculation, and I will use average force to calculate the work I've done. So now let us calculate the work is equal 500 Newton multiplied by 0.1 meter, which will result in 50 Newton meter. And Newton meter, if we multiply them as scalar product, we call this unit joule, right? So 50 joule. So again, please see what we've done. We calculated, although our idea was a bit different, but we still found actually the area below this curve. And we already know that this area is actually an integral of this function, of this line. And indeed, this assumes that if our force would depend on position in other way, for example, not linear, but maybe like this, or maybe sort of exponential, in all these cases, the work we need to find would be the integral between our 0 point, initial point, to our final point. Force, which will depend on distance, dr. So, and you see what we discovered now. First, we saw that the work is a scalar product of two vectors, the force vector and the displacement vector. And in some cases, we can simply say, well, it can be calculated as magnitude, product of magnitudes of these vectors multiplied by cosine of the angle between them. But now we made it a bit more general. So we are talking about not simply scalar product, but integral of product of two vectors, the force vector and displacement vector. But this time we made it a little bit different. So work is also integral. And in many cases, you will rather use this concept, this idea of work. There are some situations, some problem solving where you need to analyze force in terms of integral behavior. And again, we see that this is sort of very general, very essential formula, which will collapse into standard formula if you assume that Fr as a function of r is constant, does not change in time. In this case, mathematically, we can take this value out of the integral, and it will result in f integral from initial to final dr. And in this case, this integral is simply our displacement, our vector r. So the formula will again collapse into f multiplied by r. I'm not showing that they're vectors, but okay, let me show that these are vectors always. So again, what the formula we have here is a very general case, very fundamental case. And good news for us that for your problem solving in midterm, you don't need to calculate this integral, because probably in your mathematics class you are not too far. But rather, for your problem solving, you would experience this formula in more degenerated or collapsed state, where you are just dealing with scalar product of two vectors. So mostly you will experience this formula. So let me summarize. First, we saw that work is a scalar product. Second, we also saw that work is an integral of force with respect of displacement. And let us mention briefly the third aspect of work. This is the energy aspect. Later, we will see that the ability doing work depends on energy content. We say that if some object has no energy, it cannot do any work. So we will introduce energy as capability of doing work. And therefore, in our later classes, you will see that there will be very close relationship between work and energy. And we will see that energy is actually equal to the change, work is equal to the change in the energy content in the system. So let me put this formula here. So after the mechanical work is done, the mechanical energy of the system will decrease. Well, this last part, the work as change in energy, I have introduced very briefly because it will be the main topic of our class in 2 weeks. Not in 2 weeks, in 3 weeks, in fact. On 5th of January, our main topic will be the energy work theorem and close relationships between work and energy content. So this class will be given either by me or by my student Fuad, whom many of you already know, and he will or I will talk about this relationship more close. So in your homework, I would like you to think about these concepts I've introduced and apply them for solving of simple problems, which will be given to you as your next test, the test number 9. I'm not showing any solutions right now because I wish you to check those tasks, those problems, and you try to make your own solution basing on the theory I've given today, so that you can exercise your creativity and also independent way of solving problems. I'm not showing some, exemplary solutions because I think you already can do it by yourself. Let us try this way. So that was the theory for today, and the very last, the remaining part of this class, we will spend in a little bit problem solving, where we exercise some dynamics problems, and just to check our concepts. I've prepared a couple of problems for us. Let us solve maybe 2. That would be actually enough. I think solving just 2 problems would be fine for all of us, because then you will be not overloaded, because we spent a lot of time in one block and you will be tired, and I don't want to make you even more tired. And actually, I think you should slowly learn to work more independently by yourself, by working with books and by thinking. So 2 problems we're going to solve together. Let us try to do it like we did before. That means I give you 10 minutes time to solve it by yourself, and then together we check the solution, okay? So this will be our setup. Looks a bit different than what we had before, but I think you all could recognize there is a pulley system, and this time we have 3 masses. So I have M1, let it be M2, and M3. These are 3 masses. I will now write or introduce this problem in German, So, zwei massenlosen Scheiben und drei Körper. M1 gleich 1 Kilogramm, M2 auch 1 Kilogramm und M3 machen wir es 4 Kilogramm schwer. Okay, also diese zwei massenlosen Scheiben und drei Körper werden zusammen verbunden, wie auf der Abbildung, und freigelassen. Freigelassen means that we just put these masses, we just hang them on the rope and we let it go. So we leave it at, rest. So we just do not apply our forces. And the aim is to find what is the acceleration of the mass m1. So again, please let us try to do it first by yourself. Take your time. I would say 10 minutes should be enough. You have everything what you need. You have all masses, m1, m2, m3, and the goal is to find the acceleration of m1, in which direction and how big is the magnitude. It is not a problem about work, okay? So this is a dynamic problem. So we are repeating the previous material, the previous class. You do not need to apply the concept of work. You just apply the second law of motion. And let me motivate you additionally. So the one who will give first the correct answer will receive additional bonus points from me. I am recording your performances and I'm collecting your bonus points so they positively contribute to your Zombie node. So the one who will solve this problem first will receive additional bonus points for your Zombie node. Okay, please go ahead. And in 10 minutes, we will discuss your answers and the solution. So, okay, I see there were some answers already. Thank you very much for these answers. I think some answers are correct. And some not very correct. Let us check together. And I think okay, but I don't know why, Mom, you changed your mind now, because your first answer was actually looking better to me. But let us take a look, okay? So let's check it together so that we make clear that every step we do is reasonable. Well, first of all, before we start drawing forces, let us make clear that, in fact, we have here not one single rope, but two. Have you noticed this, right? So we cannot just say that we have tension equal everywhere in the whole rope system, but rather there is this rope, and its tension here will be obviously, let's call it T1, and it's not necessarily same tension as we have in this rope, because these are two different ropes. Do you see it, right? They are different because there is a mass between them. And by the way, I'm pretty sure that T1 and T2, they will be not identical to each other, because otherwise the mass M2 would not maybe move, or it will just move just by free fall, which is not very probable. So this is the first consideration I would suggest, that we see that in our system there are actually two different tensions. Or if you wish, I can also say that also this tension is also the third one, yeah? Which is an additional. Now, you can, if you wish, you can call it also T3. Now, after we made this initial analysis, this initial consideration, I see there are some more answers arriving. Thank you for that. Looks also good. Yeah, we'll check it. So, what about forces, right? So we say again, first step we do is forces. I will put them just directly on the diagram. So that will be our mg and 1g. Well, if I call the tangent of my red rope T1, then all of us know that this tangent here must be, guess how much? I think you know, it should be twice T1 because of this pulley system, right? So what about, and it acts upwards on the body M2, M1, sorry. So what about M2? Here we have three forces. It experiences tension, which pulls it downwards, T1. It experiences tension T2, which pulls it upwards. And of course, the M also experiences gravity, so we have M2G force, which is, of course, also downwards. So M2G. And finally, with the mass M3, I think this is the simplest because it's only T2 upwards and M3G downwards. I think this should be okay. If you notice something wrong, please let me know. And now, after I made this analysis, I'm ready to apply my axis. Actually, I need just one axis, since all bodies they move only in vertical direction. I am not interested in this direction at all. I don't need to introduce it. Since all bodies, they move either upwards or downwards, I will just choose one direction. And you are the boss. You can decide which direction will be your upwards direction. So for example, your positive direction. So I will choose maybe, yeah, let me choose this direction as, let me see, what will be simply, yeah? Actually, up, I would choose positive, just it makes it a little bit simpler. So that would be plus. But basically, it doesn't matter. It doesn't play any role. Okay, after I decided which direction will be positive, I'm ready for the next step, and this is application of the second Newton's law, right? Which is sum of all forces will result in acceleration of my body. So let me now apply it for the body M1, M2, and M3 again. For M1, so positive is here. So for M1, I will say 2 times T1. This is my blue part, minus M1G results in M1A. And this is the acceleration I'm searching, I'm looking for, right? Let me label it gray. This is what I want to find. So what I can say about M2? Well, in the case of M2, upwards is acting T2. It is positive, T2. T1 is pulling downwards. That means it is minus. And gravity is also acting downwards. So that's why we need to put it here, M2G minus. And it will result in acceleration of this body MA. And here I want again you to be careful, because think about again how the system is moving. We already made this setup when we have two bodies. Let me draw it here. The one that moves like here and another which moves here. And we notice that acceleration here is not equal to acceleration here. They are not equal. A1 is not equal A2. You remember we already made this. And if you have such a setup, this body will move slowly, twice as slow as this body. So please just don't forget about this. And in a pulley, if we are talking about acceleration of mass M1 and acceleration of mass M2, they will be different. And in fact, the acceleration of the mass M2 will be double of the acceleration of mass 1. So that's why I need to write 2 here, because this body, M2, let me make it red, it would move 2 times faster than the body M2. Again, I already tried to explain the reasoning for that, but we will mostly clearly see the reason for that in our later class, as we will talk about conservation of energy. Finally, we are ready to write this equation for the mass M3, which is the simplest one. M3G minus T2 results. Again, please remember we are dealing with doubled acceleration as compared to M1. So that's why, again, also here we have 2. M3, and we have again A. So it's same A, but we considered that the accelerations are slightly different if we are talking about bodies M1, M2, and M3. And now I have a system of equations, and my final step in the solution will be just to put it together in a reasonable way, such a way that
all tangents possibly disappear from my system and I can solve it for A. How exactly you solve for A, it is actually entirely your business. So you can maybe have some tricks that allow you to solving such systems of equations. Maybe you have some nice algorithms or your own strategies. It is really up to you. So I would here use, again, addition and subtraction of the equations in order to eliminate the t-values. So what I will basically do, I will take the equation number 1. I will add to it the equation number 2, but before I will double all the values here, left and right, and then I will add the equation number 3 to them, but also I need to double off values. Do I need? No, I will not double. So I will add just this. So I will just add them all, this plus this plus this, but all values here I will need to double. Okay, what I will have in the end, if I solve it for A, it will be like this. A is equal G 2 times M3 minus 2 times M2 minus M1 divided by 4 times M3 plus 4 times M2 plus M1. Your solution may look different. This is fine because it depends on how exactly you calculated, you solved it for A. But I think mathematically it should be more or less equivalent to this solution I got here. And now if you put the values here, I will get something like 50 divided by 21, which is pretty close to 2.338 maybe meter per second squared. So that means the very first answer from BAM, I think that was fine. And Emmanuel, let me also check if I say 12 divided by 5. Let me think. I'm getting also pretty close there value, I would say. Just let me see. 12 divided by 5. 2.4, great, yes. So also the solution from Emmanuel was also pretty close, very good to, solution. Great, at least the feedback I got from some of you, it looks really encouraging, it looks good. Thank you for sending me your feedback. And again, don't worry if it's wrong. It is wrong sometimes. Also, I'm doing mistakes, so don't worry about this. But I just need a little bit more feedback, communication from you, so the more answers I get, the better. So let me also encourage the rest of our group also to send me your answers. Again, I will not use them in negative sense against you. If your answer is wrong, it's not bad, it's not catastrophe. Well, great. So let us check it one more time, briefly. So that was our problem number 1 out of 2. And I hope, meanwhile, it should be clear to all of us that the strategy we've introduced is actually quite successful. It is working. So these simple steps I'm repeating again and again, drawing forces, defining the axis, writing Newton's second law, solving for the value or unknown value, it works pretty well. Just we need to pay attention about what are the forces, what is the system, how do we you know, what the accelerations in the system are, and then everything is fine. Now, I have one more remaining problem for today, the last one. I hope you can still remain concentrated, and I request you kindly to remain concentrated for one more last problem. Let's call it problem 2, because this problem will be new for you. It will be a new concept, and it will be a problem which you probably have never met before. So it will be, I will call it a helicopter problem. So, okay, so this thing I've thrown, if you could recognize it, but I hope you could recognize it as a helicopter, maybe a strange one. And in this helicopter, we will put a rope, and on this rope, we will put some cargo. But this time, I will make my rope to have some weight. So this will be very new, and maybe you have never solved problems like this. My rope this time will have mass. So let me introduce what we have in our system. Let it be the mass of cargo. Let me call it MC and cargo. We have mass of the rope, MR. We will have some mass of the helicopter. Let's call it MH. And what helicopter does, it of course applies some lifting force, which is the force of the engine. Let's call it F lift. The question is to find out the tangent in the rope. If, assuming you know the lifting force, mass of the helicopter, mass of the rope, mass of the cargo. And at that moment, you should actually say, no, wait a moment. Since my rope has mass, you cannot ask about tangent in the rope. Why? Because it will be different. If I measure tangent here, and if I measure tangent here, they will be not same. Do you agree that they will be different? Do you see it? The reason is that if you measure tangent here, then it will be actually less than tangent here on the upper part, because the rope is also heavy, it has mass. And it means that if our rope is going to rupture, it would rupture somewhere here in the upper part and not in the lower part, because the tension in reality depends on the height, depends on the position. You see, we are trying now to approach not ideal problems, but real problems. Well, but what should I do? Well, let me then ask it more precisely. What will be the tangent in the rope at the distance B from helicopter? So I will specify this length. So the whole rope will have length L. And I want to know tangent in this particular point, point B, because I think this point is critical. Maybe I know that my rope is not strong enough and it might rupture here where I have some break. And I'm wondering, is my tension at this point, is it low enough or will my rope rupture? So I know the distance B. I want to know how big is tension at this point. Let's call it TB, tension in the point of B. Do you see that this problem is sort of unusual, right? And seems to be tough, seems to be hard. And it is yes and no. It is hard and it's easy at the same time. So some question came, just let me see if the rope in another scenario is horizontal, will the tension then be equal? Yes, in this case, if it is horizontal, then you're right, then it would be at least in the part of the rope that remain horizontal, the tension will remain same, right? But if your rope will have some hanging part, you know, in the vertical direction, then the tension will be highest in the upper part, so in the highest part of your hanging rope, right? Because if you move upwards, the weight you have to carry is bigger and bigger, right? So I think we can see it. Okay, so you see, let me explain why it is hard and let me explain why it is easy. It is hard because if we do it in a classical way, that means we say, okay, there are three masses here. I have mass of the helicopter, I have mass of the rope, I have mass of my cargo, and I just need to make my force diagrams, and I need to make the forces acting, and I need to make axes, and I need to apply the Newton's second law. So this approach will not work. It will not help us because we will not be able to find tension in this particular place, in the B point. It will not work. But why is this problem easy? It is easy because if we do it a little bit differently, then we can use our usual approach. Let me explain what the main trick is here. Since we are asked about the tension at this particular point, we need to define masses in our system in a new way. So instead of using mass of the helicopter, mass of the rope, and mass of the cargo, you should introduce new masses, new divisions in your system. You need to divide your system in precisely two parts. You need to put your boundary here. And then all masses that are below this boundary, you will call mass down. And all masses that are above this boundary, you will call mass up. Or you can call them more interesting, more sexy if you wish, but I will call them M up and M down. So that means my M up is equal mass of the helicopter plus the mass of the rope, but only part of it, you see? So just this part, this red part of the rope, let me make it blue. The blue part of the rope, this mass, I need to consider. How much is this blue part? How much is its weight? It's quite easy to find. Look what I'm doing. I will take mass of the rope, of the whole rope, divide it by the whole length of the rope, and then I will multiply it by the B length. It will give me the mass of the blue part. So that means I'm taking just fraction of the mass of the rope. For that, I will first take the whole mass of the rope divided by the whole length of the rope. And then this value I will multiply by the length of B, and this will give you mass of the upper part of the rope. So that is my mass up. What is the mass down? It is the mass of my cargo plus the remaining part of the rope, right? Or the remaining part of the mass of the rope, which will be mass of the rope multiplied by then 1 minus B divided by L. So it's just the remaining part, 1 minus B divided by L. Okay, that's it. That was the most critical, most important step, and I wanted to teach you to do this because the rest is easy. The rest is sort of very simple. We defined now two masses here, and after we've done this, the rest is exactly same as we've done before. That means now we just proceed as usual. We will define forces that are acting on our masses, and we will solve it in a usual way. Let us do it. So what are forces acting on the upper part of my system, on the upper mass? So what are forces acting on this system, which is above my boundary? It is the lifting force that acts upwards, F lift. And this is tangent TB, which I'm searching for. I'm looking for this tangent. It is acting downwards, TB. And in addition to the tangent TB, there will be also, of course, the whole gravity, right? So gravity of my system, which is M up G, M up G. Okay, now I think I have all forces that act on my upper system. It is lifting force upwards. It is the gravity force, and it is the pulling force of the rope, and it depends on my lower mass. But I do not need to take the lower mass. It is here as TB here. So three forces. Okay, what are forces acting on the lower part of my system? I think that's quite easy. There are just two forces. It is gravity, M down G, and it is the TB again, but this time TB is acting upwards because it is pulling my lower fragment upwards. And that's it. So now we are ready to go to the next step. Let's define the axis. We've shown all forces. Let's define the axis. Well, I would say let's choose upwards direction positive. Although it doesn't matter, but let me choose this positive, upwards. And now after I did this, I'm writing the second Newton's law for M up and for M down. So let me do it for M up. So lifting force, F lift, minus tangent at point B, minus the gravity force, M up G, result in some acceleration M up A. By the way, I have no idea if this acceleration is upwards or downwards because I'm not given the lifting force. If my helicopter is strong enough, I will find out that my acceleration may be positive. But if it's not really strong or if it's descending, then I may find that A is negative. I don't know, but it doesn't matter. So what about M down? So that's more easy. So it is TB minus M down G equal M down A. It's same A because they move together, right? So there's no difference. It's a whole system. It was our artificial division. So we put the boundary artificially, but actually it's a whole system. It has same acceleration everywhere. Well, and that's it. Look, what we have is a good news because we have two equations and there are only two unknowns, TB and A, we don't know. All the rest we know. And that means we can solve it. And after we solve it, we got our solution. We can find the tangent of the rope. And if you wish, you can also find the acceleration. Can be solved. I don't want to solve it now because I haven't given you any numbers, but believe me, since mathematically there are two equations and two unknowns, we can solve it. So let me summarize, because I think slowly we can finalize today's class. Let me summarize what we've done today. First, we talked about your homework assignments, and again, let me make a pressure on you. I will be waiting for your solutions for the next test. So please take it serious. Please give me more feedbacks, because at the moment I'm orienting myself on only students who send me their solutions, so I can judge about their strength and I can adjust this course depending on their feedback. But if you are responding nothing, I have no idea if you are too good that you find all problems too easy and stupid, or you're too weak and you need much more help from me. But as you are not giving the signals to me, I will just use the feedback I will get. That's it. Second, we talked today about work. I haven't spoken about power. This we can do actually next time. But we talked about work in different aspects. We saw that work, physical work, is a scalar product, and at the same time, it is an integral of force with respect of distance, of displacement. And we also saw that work is the change in energy of the system. And finally, we've exercised a little bit in problem solving by using second Newton's law. And in the end, I hope it made fun that we addressed some totally new problem that you mostly don't find in your handbooks. And this is a problem which is sort of advanced problem where objects like ropes have mass. And you saw that some approaches we developed before they work, but you need to be more careful, you need to be creative, and you need to use your fantasy and imagination to solve such problems sometimes. And that's why we're doing such things. Still summarizing, I hope today's class was, well, not very boring for you and also useful for you, that you learned something new. Thank you for your attention, and today I will send the video and the materials from today's class to you, both per Ilias system and over EduPage. And please don't forget about solving your next homework, the test number 9.
It will consist of maybe 3, 4 little and simple exercises. I will still remain in network in case you have any questions or any comments. I will remain in chat, maybe 5 minutes long. But to all of you who already have no questions and ready, again, have a nice week, and we see us next Tuesday again. Have fun and stay healthy. Goodbye.